let's go ahead and get started with our next talk. So I would like to welcome Jonah Gaster, who will be telling us about vertical arcs and the Markov Uniqueness Conjecture. Take it away.
Yeah, thank you so much, Molly, for hosting, and thanks for listening, everybody who's here, and for putting on this conference. I'm going to tell you about the Markov Uniqueness Conjecture. So the Markov Uniqueness Conjecture concerns, oh, by the way, if you have questions or anything, feel free to holler. I can't see the chat, so you'll have to let me know if you have any questions. So Markov Uniqueness Conjecture is about integer solutions to this simple cubic equation called the Markov cubic. When you have a triple of positive integers that satisfy the equation, they're called a Markov triple. So for instance, 1, 1, 1 is the simplest Markov triple. The conjecture asserts that if you have a pair of Markov triples with the same largest entry, then they're the same triple. So in other words, Markov triples are parameterized just by the largest entry. The Markov conjecture itself, I think, has been kind of regarded as an attractive curiosity that seems related to lots of other things. It has manifestations in geometry and arithmetic and combinatorics, Diophantine approximation. The numbers themselves are just ubiquitous. I mean, there's something really beautiful and fundamental about them. Unfortunately, this problem in particular is so old, it's kind of infamous, and it's one of the prominent problems on this list that's called "Don't try to solve these problems." So it's the kind of problem that people generally stay away from because of how old and simple it sounds. It's probably very, very hard. But anyway, I think it's a beautiful opportunity to learn some math. So I hope to convince you that there's beautiful stuff going on here, even if we don't solve the conjecture. So your first guess, if you were trying to approach this problem, your first problem would be to try to understand the Markov numbers. How could you parameterize them? How could you list them? And the reason that you can kind of do that is because there's a very pleasant symmetry to this equation. If I fix two of the variables like x and y, then I can regard this as a quadratic in Z, and I can flip one solution in Z for the other. And when you write that out explicitly, here's what happens when I fix y and z, and I flip the solution for x. The other solution looks like 3yz minus x, another integer solution. So for instance, if I take 1, 1, 1 and I perform that move, I get 2, 1, 1. And if I take 1, 2, 1 and perform that move, I get 5, 2, 1. So you can think of that as a kind of graphical move. When I have a triple x, y, z, I can fix x and y and switch z for 3xy minus z. So here I've started tracing that out a little bit. I start with 1, 1, 1, I get 1, 1, 2. Then I fix 1, 2, and I do 3 times 2 minus 1, that's 5. Now I have 1, 2, 5. I can either fix 1, 5, and I flop 2 for 13, or I can fix 2, 5, and I switch 1 for 29. And you can see how I'm filling out the entries in this big tree. So to fix some notation, T is going to be the name of this rooted trivalent planar tree. And because it's planar, there are these complementary regions that you should think of as horoballs. This is coming from the fairy graph in PSL2Z, which is secretly lurking behind here. But these are what I mean by script H, these horoball regions. And the upshot of this whole story that I told you up here is that there is a labeling, a Markov labeling. So if I take my collection of horoballs, the flip move that I told you, and starting with 1, 1, 2, provides information for how to fill out the labels on the tree. So I'm getting a map from H to M. And because I started with a Markov triple and I'm applying this move, all the numbers I find are Markov numbers. So that's why the image is M. So it's not too hard to work out that this map to M is actually onto. Every Markov number will appear in this tree if you set it up the way we did up here. And that's just because if you have a Markov triple and you flip its largest entry, you're going to decrease the size of the largest entry. So that'll sort of bring you back down to the root. And you find that you'll see every Markov number in the tree. That's why it's onto. It turns out that the conjecture is equivalent to the statement that this is actually a parameterization of the Markov numbers. So really, you can think of the Markov numbers, modulo this conjecture, as the labels on this tree. You're not overcounting at all. Okay, so So how would you do something like that? Well, I have no idea, but you might guess that this should be related to other obvious labelings. Like, for instance, the first thing I could do is maybe I think that Markov move where I see xy and 3xy minus z, excuse me, that's kind of complicated. So maybe I should simplify the story and just replace it with the simplest thing possible, just addition. So if I start with 1, 1, 2, here I would see 3, and 4, 5, and so on. I'd fill the labels out in a much simpler way. Really what I'm seeing with this Euclid labeling is a kind of visualization of the Euclidean algorithm, if you think about what happens when you go back down to the root. But the Euclid labeling forms just half of the fairy labeling, which is maybe even what was screaming out to you when you saw this trivalent tree. The fairy labeling is what I see if I were to start with these fractions. I hear there's something arbitrary about how you start, but I made a choice here. So here's 0 over 1, 1 over 1, and 1 over 2. And now I'm going to fill in the labels on the tree using fairy addition. And of course, here I would see the Euclid labeling as the denominator of the fairy labeling. So those are other natural labelings on the same set, natural functions on the same set. Why would you guess that they're related to the Markov labeling? Well, because in the Markov labeling, you know, I see things like this as I go down the tree, but if I were to take logs of everything, then up to some error that goes away as the numbers are growing, this really looks like I'm just doing addition. So somehow the Euclid tree, the Euclid labeling looks like the Markov labeling after you take logs. And that was actually proven by Zagier in an important piece of work where he counted Markov numbers up to a certain bound. And he really got a lot of juice out of this fact that Markov numbers up to a multiplicative constant are just like the Euclid numbers. Let me point out before we go on here that, well, so we're trying to show, or we're dreaming that somebody's going to show that lambda n is 1-to-1. Well, we can make an obvious point, which is that the fairy labeling is definitely 1-to-1. And if you'd like the kind of proof you could do with people when you first introduce them to the fairy graph is there's a planar ordering on these horoball regions that it inherits from being in the plane. And the fairy labeling you can check using like fraction stuff is respects this ordering. So it has to be 1-to-1. Okay. Yeah, so there's something important going on behind the scenes here that Zagier was exploiting, and that won't be clear yet, but I'll tell you about how hyperbolic geometry enters the picture in a moment. And when it does enter the picture, what you'll see is that the Markov number is essentially like the exponential of a hyperbolic length of something. And what Zagier is saying here is that hyperbolic length and arithmetic length are roughly the same in whatever sense that means, which will be clearer in a moment. In fact, you could tighten all of this story, which was investigated by Vladimir Fock. You could take, instead of approximately hyperbolic length, you could take genuine hyperbolic length. And then when you take this ratio, you get a very beautiful decreasing convex function, which is related to some beautiful work of McShane and Riven on what's called the stable norm in the homology of a punctured torus. So there's a beautiful story behind the scenes here, which is just entering the picture of hyperbolic geometry. But before I turn to hyperbolic geometry, let me just say, to motivate my main theorem, it's a bit contrived, but you could ask, well, you see the Euclid numbers are the denominator of the fairy numbers. So somehow the Euclid labeling can be improved to a fractional labeling where there's a numerator. But the Markov numbers are just integers. So where are the numerators when I go to the Markov numbers? So Euclid numbers, arithmetic length, Markov numbers, exponentials of hyperbolic lengths. What happened to the numerators? Is there a fractional Markov labeling? And indeed there is. So to tell you about it, let me introduce one of the reasons that people love the Markov uniqueness conjecture. It has deep connections to geometry. So namely, the connection goes through what's called the modular torus. So it's a very specific punctured torus whose fundamental group is a subgroup of PSL2Z. That's why it's called modular. In fact, it's the commutator subgroup of PSL2Z. It's a very very beautiful subgroup of PSL2Z. If you want to know who it is, it's kind of what you would guess. The first time you tried to build a hyperbolic punctured torus, your first guess would be to do something like this. You take a very symmetric looking ideal quadrilateral in the hyperbolic plane, and you try to make guesses for side pairings that are as small and integral as possible. And if you do that, you'll find these side pairings work beautifully, 2, 1, 1, 1, and 2, -1, -1, 1. And those elements generate the commutator subgroup. So that's the punctured torus that we're talking about. That's the modular torus. What's the connection with the Markov numbers? Well, it turns out, by a bit of magic involving the SL2 trace identity, whenever you have a trio of simple closed geodesics on a punctured torus, in particular on the modular torus, that pairwise intersect once. So that means that they're relative to each other, they're in very simple position. They all pairwise intersect once. They have 3 curves. They determine 3 elements of PSL2Z. Okay, then I lift to SL2Z. I get 3 traces. Those traces, alpha, beta, gamma, because of the trace identity of SL2, turn out to satisfy this simple equation, alpha squared plus beta squared plus gamma squared equals alpha, beta, gamma. So that looks like the Markov cubic, and it almost is up to a factor of 3 that's missing. But what it means is if you have such a trio, then when you divide them by 3, then they satisfy the Markov cubic. And in fact, what you can find is that the traces of simple closed geodesics on the modular torus are precisely 3 times the Markov numbers. Right. And so with this translation to the modular torus, the Markov uniqueness conjecture becomes the following natural geometric statement, that if I have simple closed geodesics on the modular torus of equal length, then they have to lie in a common symmetry orbit of the modular torus. Okay, so a kind of natural question that I started this whole experience with was, what about simple arcs? So in some sense, it should be this kind of same story. Here, when I say simple arcs, I'm talking about simple proper geodesic arcs on the modular torus. So I have geodesic embeddings of R into the modular torus with both ends that go out the cusp. In some sense, you might expect this story to be exactly the same as for simple closed curves, and it kind of is, but I think that there's some more juice, there's something convenient happens for arcs that is harder to see for the closed curves, which is kind of part of a general story. There are several problems now. I learned about this from Piotr Przytycki, who has some beautiful results where you take a question that's very difficult, a combinatorial question about simple closed curves, and it turns into something tractable with beautiful answers about simple arcs. So what can you do with arcs on the modular torus? Well, when you have a proper geodesic arc, you can lift it up to H2 in many different ways. But if it's proper, then both of its ends have to accumulate on cusp points or lifts of cusp points up to H2. Now, there's only a single cusp in H2, so I can get all the cusp points just by hitting this one cusp by elements of the group for X. And it turns out to you just find PSL2Z times the point at I infinity, which is to say all the endpoints have to be on the rationals, the completed rationals with infinity. So if I take a lift which is vertical, one of its ends goes out to I infinity, the other end has to hit a rational. So that is to say that I'm going to find vertical lifts of proper geodesic arcs on X. And I can parameterize those vertical lifts just by their real part, which is a rational number. So that means there's a kind of convenient picture, excuse me, there's a convenient picture for vertical geodesics that are proper on X. Modulo isometries of X can just be parameterized by rationals between 0 and 1/2. That's because I had any vertical geodesic arc, I can apply covering transformations and symmetries to a range that it lies in between 0 and 1/2. The problem is that this obscures which of them are simple. That's actually the whole difficulty of this problem, is captured by the simplicity question. So let me tell you the main theorem here, which I probably won't talk about the proof at all. It's a hyperbolic geometry exercise. It turns out being a Markov number is equivalent to the statement that there is some numerator k, so that the arc with real part k over n projects to a simple proper geodesic arc on the modular torus. That's actually a characterization of being a Markov number. Let me say that it's not surprising that that being a Markov number would say that there's some sort of arc that is simple, because as I already told you, Markov numbers are traces of simple closed geodesics. So you could just, for every simple closed geodesic on the punctured torus, there's a unique simple arc disjoint from it. So there's clearly some rational number associated to that n. What's surprising here is that it's so simple. The denominator is just the Markov number n. It's not some strange function of n. Okay, so that's saying something about the Markov numbers. I think it brings up more questions than answers. The basic question is, well, what is k? What can you say about k? Where does it come from? What is it saying about the Markov number? And let me tell you something simple. So what you can say without too much difficulty is that the square of k is -1 modulo n. And a proof sketch of that is, well, all these simple proper vertical arcs are necessarily preserved by the elliptic involution downstairs. So they're a subset of the elliptic vertical arcs, which are a subset of all of these vertical arcs. And being an elliptic vertical arc can be characterized, in fact, this is an if and only if as well. Being preserved by the elliptic involution downstairs is characterized by having the numerator square to -1 mod the denominator. So this is not too hard of an exercise to work out. Again, just using PSL2Z, you can do this very concretely. You can turn a geodesic around using an element of PSL2Z, and you can study what it's telling you about P and Q, and you'll find this kind of thing. But I would say that I find this quite mysterious. It's not hard to work out, but I don't understand why is multiplication in Z mod NZ relevant. That seems a little surprising. And I can't tell if there's something deeper going on that explains this, or if it's some kind of accident. It's tantalizing because there's so much structure to simple arcs. So what are some consequences? Well, the first thing to say is you can learn about how non-injective the Markov labeling might be just by counting the number of roots of -1, because the isometry orbits are sort of determined by this rational number between 0 and 1/2. So you just need to know how many different numerators could I see. In particular, when n is a prime power, there's exactly 2 roots of -1, and there's only one of them less than a halfway along n. So what you find is Markov uniqueness conjecture holds for prime powers. That's not a new statement. That's been known for a few decades. That's kind of the easy case of Markov uniqueness. But here we're just demonstrating it from the point of view of geodesic arcs on the modular torus. You also get a fractional Markov labeling that I started off asking about. The denominators are the Markov numbers. The numerators are the k's that come up. And you can be very explicit about how to construct this using, flipping triangulations. And let me not say any more about that because I'm almost out of time. It's also not too hard to work out for the same reasons that the ferry labeling was 1-to-1. This fractional Markov labeling is also 1-to-1. Okay, so let me just finish. I have 1 minute to tell you about questions that I'm curious about. The most basic one is, how do you say who K is? That's really getting to the root of the MUC, so it has to be a hard question. It's kind of as hard as MUC. But I think there's other things to ask about. So here's one thing that explains the picture behind me. You see, what you're looking at right here is a function that takes P over Q, a rational number, to the Markov. So I look in the tree where I see the fairy label P over Q. I see a Markov number there. And now I'm going to take log n, log of the Markov number, which is giving some version of hyperbolic length for this simple proper geodesic arc corresponding to n. And the beautiful thing in the picture is that you can see there's like amazing linearity that I don't understand. It looks like you're just sort of taking the plane of relatively prime P over P comma Qs, and well, you can see it. You can see all of the lines, and you can see sort of prime gaps, and I think it's a beautiful picture to try to understand more. So sorry for going a minute over. I'll stop there.
Thank our speaker. Oh, great. Any questions for Jonah? We have one in the chat, Jonah. In the statement of MUC, there is a maximum. Can you say what that maximum translates to in the geometric side?
Yeah, that's a good question. So, so the way I described MUC was you look at this labeling and you worry that there might be two different occurrences of a Markov number. Well, whenever there's an occurrence of a Markov number in a horoball, just because of the way the numbers behave around the horoball, I could find the highest point where this label is the largest in a triple. So if there were two labels, then I would find two triples with the largest number. So in the geometric side, that's like saying, if I have a simple closed geodesic, I fill it out to a trio that pairwise intersect once, but I worry that, and then I arrange for it to be the longest of those three. Now, the worry is that it might participate in two different trios in which it's the longest. That would be the failure of MUC. MUC predicts that for every simple closed geodesic, it's the largest of such a trio in one way.